So there will be no chemical engineering without separation, because the fact is that most reactions in the world are not complete reactions. They happen partially. So like the SMR reaction I showed just now, the water gas reaction, it happened partially. And when you have a reaction which happens partially, we need to be able to separate the unreacted reactants and the product. Otherwise, how do we sell the product? We can't just take the whole thing and sell to your customer, right? The customer is wondering why you have like so many other things that they do not want in the product you're selling them. So separation is key. And obviously, HYSYS supports separation processes. The common ones are distillation, stripping, adsorption, liquid extraction. And these are usually modeled by columns. These are usually modeled via columns. We also have adsorption, which is the physical separation process, which you can't really do very well in HYSYS because they don't. Adsorption is normally a batch process where you have multiple vessels, and then you run one vessel in adsorption, and then the second vessel is on regeneration and so on. So that's not something you can do easily in HYSYS because HYSYS is only a steady state simulator. You can also do membrane separation, but you have to program the membrane details yourself. And I think membrane separation is starting to gain traction as more and more people in the industry do like membranes. So let's go to case study 4. So Dave's yet another colleague. Dave has a lot of colleagues today. His name is Klutz, and he's required to design a new N-octane production unit. So octane is a component in petrol, and let's assume that because people are driving more nowadays after COVID, after lockdown and lifted, and there's more demand for petrol. So this company is thinking of producing more petrol. So this will be something like an expansion project. So this unit will produce N-octane from ethylene and iButane as the following reaction. 2 molecules of ethylene plus iButane to form N-octane with some nitrogen and N-butane as inert in the feed, which for some reason or other cannot be removed before entering this reactor. And this reaction is also a reversible reaction. It's quite common that most reactions are reversible in the world. The unit shall be modeled as a combination reaction and separation unit as follows. I'm going to give a conversion vector, which is a very simple reactor type. And then I'm just going to use a shortcut distillation column. If you have more time, you can go into like the more detailed kind of distillation column. Okay, so let's start out with the conversion vector setup. So let me just keep this, make it smaller, and I just open my new case. Just ignore this old case for now. Well, I think I should start closing up the home cases. Okay, so let me just add in the components that we have. So we have ethylene, N-butane, iButane, and octane. It's not this. Ethylene. Let's start another name. T. Why you give? Just T2H4. No, still not you. No component match. Cannot be one. Yes. We just add the other components. It's annoying. Let me just delete. Sometimes annoying HYSYS is that it just hangs for no reason and then you just don't show the component that you want. Let's see. Ethylene is here. Wait, where do you go? Okay, finally I got you. Italy. Then we have N-butane. We have iButane, isobutane. we have N-octane, we have nitrogen as the inert product, and that should be it, 5 components. The package, I'll just go for pancomycin again. I can go for SRK for this, but yeah, there's not much difference in that. Then go to simulation mode, start dropping in the stream. I'll just call this, let me see what name I used previously. Let's feed then. Let's call it feed. And the conditions that we need are 93 degrees Celsius and 20 psia. So that will be 93 degrees Celsius, 20 psia. And let's give it, in this example, I define as kilomole per hour flow rate. So I don't have to give the total flow anymore. I just directly go into the kilomole per hour flow rates. Just put this in here and put this in here. Sorry, this one should be. Let me just check this screen here. And okay, so the Italian will be 20 kilomole per hour. So this one I set to mole flow. Unit is kilomole per hour. Okay, 20. And butane will be 0.5. Butane will be 10. And octane will be 0. Nitrogen will be 0.1. So 30.6 should be the same number here. Okay. Letting our model palette go. Okay, it's on the right side of the screen. Okay, draw a conversion reactor, which is here. The conversion reactor basically just takes an equation and it just specifies the conversion without actually calculating the equilibrium or the rates. So it's only good if you are guaranteed that you know what the conversion is. So with outlet, I'll just call it a product V for vapor, product L for liquid. Then go into reactions. Again, we need a reaction set. So let's go back to properties, do a new reaction set for this document. Reaction. This will be just a conversion reaction where lysis will not calculate any kind of kinetics. So the reaction is just 2 C2H4, so ethylene, the first one, -2. C4H10 is N-butane, -1. Product, N-octane. So that's one. So balance is no error. So base component here will be, let's put, can't remember which one's the limiting method. Conversion will be put at a number, let's put it as 98%. So C1 and C2 are temperature dependent. So in this case, we are just fixing the conversion at 98%. So I not really care about the temperature. So just add to full package. Go to simulation. Now I can put in here. And the reaction is completely satisfied because I've already defined the required reactions. And you can go back and have a look here and then go through. So if you calculate the composition, this will be a 98% conversion of ethylene. And butane is completely used up. So we have like product. Oh, I think I made a mistake. It should be N-butane should be limiting. Ethylene is the excess reactant. Okay, this one should be the correct one. And yeah, technically it's a meeting return, Tallinn access return, so we still have a lot of Tallinn in the product.